Hello to everyone that's watching, and welcome to our discussion on the retrospective InSAR analysis over the Jagersfontein tailings failure. My name is Adrian Jonson. I'm the Managing Director for Africa for Terra Insights. I'm joined by my colleague Jon Leighton from 3VG. Jon, would you like to please introduce yourself?
Hi everyone, Jon Leighton here. I've been doing InSAR for about 20 years now, and 11 of those with 3VG, the past 11, and prior to that in academia. And before that, I was a surveyor, in a geodetic surveyor in the army.
Great, thanks, Jon. So as I'm sure many of you would have heard in the news, on the 11th of September last year, there was another devastating tailings failure, which again brought the world's attention to tailing structures and the really destructive effects that you can have when things go wrong. My colleague Jon has done some excellent analysis using available satellite InSAR data, and he's going to showcase his findings for us now. Before I hand over to Jon, just a quick bit of background on this mine. It's a diamond mine based in the Free State province of South Africa. It is in fact the largest hand-dug diamond mine in the world, with a history dating back to the 1870s. The tailing structure in question only became prominent in size from 2010 onwards, and Jon will share more information on this during the discussion. So over to you, Jon.
Thank you, Adrian. Yeah, and we can see the optical imagery here over the years. There's actually a large gap from 2010 to 2017. We don't really know what happened then. But even since 2017, there's quite a lot of changes, especially on that south wall. And you can see those three white polygons, they indicate the areas where the tailings was breached in this image here. Here's our area of interest. This is Jagersfontein's in the Free State province. Let me know if I got that wrong, Adrian. The Free State province of South Africa. And on the right here, you can see there are two Sentinel-1 footprints, satellite footprints that cover the area. Here's how the satellite views the site. As I said, there are these two footprints, and they are independent. They're acquired on different days, and they look at the ground at slightly different angles, but it's reasonably close. And you can see in the bottom, the data continuity plot showing that data is excellent for both of these footprints. And Sentinel-1 acquires data on a sort of 12-day cycle in this part of the world. And as it's acquiring data, it's flying north and looking east. So many areas of the world will also receive data where the satellite is flying south and looking west, but that's not available here. But there is nevertheless excellent data continuity all the way back to 2015, I think. And this resolution, this data resolution, is about 15 meters, 5 by 20 meter sort of rectangular pixels. So think of that as about 15-meter data. And as I mentioned, there's nothing looking from the west. When you have those two footprints, you have sensitivity to displacement on more slopes and you have better coverage. But here, despite the limitations of this data set, I think you'll see that there's nevertheless good value here. And when I chose one of these footprints, there wasn't really much to separate them. So in the end, I took the 43-degree data purely because it seemed to have, on average, slightly less noise. Maybe we were just a little bit luckier on the acquisition days with the ground conditions, etc. So I took the 43 days, but we'll still talk about the 33 later on. Yeah. Before we get any further, let's just talk about InSAR resolution. And when I say InSAR resolution, I'm really talking about the resolution of the results rather than just the source data. And on the left, you can see a TerraSAR-X, commercial TerraSAR-X result or heat map over an area. This is nothing to do with the Jagersfontein. But on the right is a date-for-date comparison of the same heat map using Sentinel-1 data. And TerraSAR-X is around 3 meter source resolution. Sentinel-1, as I say, is about 15 meters. And you can see that the magnitudes of displacement are reasonably similar. But what the Sentinel-1 lacks is these small features here that just get kind of smudged out. But despite that, again, despite this limitation, the Sentinel-1 for this tailings dam does produce usable results. Another thing before we get going, just to make an observation really about precipitation data. So in the months leading up to the collapse, from March to July in 2022, there was quite a lot of rainfall, about 4 times as much as there was in 2021. So I'm not here to make conclusions on that. I'm not a geotech, but I thought that was worth pointing out. Also, notably, in the post-failure imagery on this area of the sort of dam here, you can sort of see these cracks indicating possibly a bulging mechanism. And this is important later on because we're going to talk about some characteristics of the displacement. And here and then I've drawn these pair of arrows in just to indicate, reiterate really the direction that the satellite's flying and then the direction it's looking in. So it's well configured to see that bulging. And here's our analysis approach. We're going to use 3VG's Displacement DataStream to analyze the data. And this is, of course, a retrospective analysis. As far as we know, that the site wasn't being monitored using InSAR, and certainly we weren't doing it. So there's a few questions you can ask in these kinds of analysis. For instance, you could ask, was there telltale displacement at the failure zone directly before the failure? But I think a much better question is to try and ask at least, what would a monitoring campaign have reported? And put yourselves in the shoes of people receiving that data. And that's a tougher thing to do retrospectively, but one of the advantages we have with Displacement DataStream is our automated engine. We can feed it data and make no special changes, no changes whatsoever actually, and just receive these automated reports with displacement in them and know that they are exactly the same reports that a geotech would have received. And we can also avoid focusing on one particular area. We're going to look at site-wide on occasion, and we're also going to go back well before the failure and see how the displacement reporting looks then. So here's our first report. This is a snapshot style view of displacement data stream, what we used to call a rapid report, and it's based on the previous 6 images. So 6 images for Sentinel-1 covers 60 days. And as I mentioned before, these white contours are the failure areas where the dam was breached. And remember also that these are line of sight measurements. Here again is the arrow and the direction that we're looking at the dam. And InSAR natively is a one-dimensional measurement. We can see displacement towards the satellite or away from the satellite. And red in this image, in the heat map, depicts displacement away from the satellite, and blue depicts displacement towards the satellite. But as you can see in this report, it's fairly noisy. There aren't really any conclusions to make from this particular report. And there's also a large hole. So you'll see these holes appear. And in general, the data quality at Jagersfontein for Sentinel is below average. But as we'll see, we're still able to form useful conclusions, I think. So 12 days later, which is the cycle for Sentinel 1, we receive another image, 27th of April. We are now 4.5 months prior to failure. And for the first time, we see this black contour here on the tailings dam. This contour is a proprietary innovation that we've worked on. It doesn't highlight the magnitude of displacement, but rather the significance of displacement. So we spent a large R&D effort to figure out how to measure noise in InSAR results. And it's quite an involved thing. There are multiple sources of error, and also there are codependencies in time and spatially that make measuring, that make dealing with InSAR statistically quite tricky. But we managed to overcome those, and this black contour highlights significant displacement, which is 4 standard deviations above the background noise. So don't worry too much about that if you're not familiar with statistics, but just to know that that is highly significant. So here we're saying that despite background noise, the displacement rises above it.
Jon, just a quick question on that.
Yeah.
On those 4 standard deviations, is this what you would normally use as an alarm level for typical projects, or was this applied specifically to this project?
Yeah, 4 standard deviations is a good default, especially for mining InSAR. So at a mine, we expect a lot of displacement, and we expect fairly high magnitude displacement. So 4 sigma works quite well in that regard. What we can do is deliver a range of contours, 2, 3, 4, 5 sigma, if people want that. And then if you consider the pipeline industry, where you have much more subtle displacement and people aren't visiting the site very much, then we might go lower, maybe go as low as 2 sigma. So that's the 95% confidence level, which sounds high, but is actually a 1 in 20 chance of a false positive. It's not actually that good. Whereas 4 sigma is much higher and generally a good balance point, if you like, for mining. As I mentioned, I don't want to cherry pick. So here is the whole monitoring area. And the point of this is to see all of the contours. Is this contour on the dam face notable in terms of the rest of the site? And we can see 2 other black contours. There's down here and this yellow polygon. And these are areas of active mining. And this is entirely expected displacement based on the activity here. And this displacement goes back all the way to at least the start of 2021 where we started processing the data, and it's there throughout the data set. So entirely expected, and not really of concern. This is not on a slope. It's just caused by settling and things like that. And you can see there's a positive and a negative area. This area is actually moving towards the satellite. And this yellow area is an area of acceleration. So here we're saying that the displacement is actually speeding up because we've compared this 27th of April report to the previous period. "12 days later, on the 9th of May, we again have a lower quality report, and we don't see any displacement detection in this report. 21st of May, the contour returns and has got slightly bigger. And then again on the 2nd of June, it's there again. So now 3 out of 4 of the last 4 reports, 3 show displacement in this area that crosses one of these breach points. So a lower and lower chance really that this is a false positive. And then again on the 14th of June, we're now 3 months to failure. And again on the 26th of June. And then on the 8th of July also. You can see it's got smaller here. I think it's not, we can't conclude that the area of displacement has got smaller because it could also be the case that there's just a detectable area. And you can see we're surrounded by some noise here. So it could just mean the detectable area got smaller. 2 months to failure. And then on the 20th of July, it disappears again. But then on the report after that, on the 1st of August, for the first time, we see a new contour appear and slightly to the west. And this is in an area of positive displacement. So this is moving towards the satellite along this vector. And this is interesting because the dam here is oriented sort of east-west, but at this point it sort of curves slightly southeast. So we would have some slightly better sensitivity here. You know, one of the persistent myths for InSAR is that it can't detect displacement on south-facing slopes, but actually it does pretty well here. You've seen these contours here. The real limitation is that it can't detect horizontal north-south displacement because it's simply not looking that way. Okay, it's looking perpendicular to that. But any displacement on a slope will likely have a horizontal and a vertical component, and it will see that vertical component just fine. But in this case, it may even see the horizontal component as well. So we have some extra sensitivity here because this isn't aligned perfectly north-south. So we're 41 days to failure and we see some positive displacement. And then again on the 13th of August, and you can see it's now larger. It's broken a little bit. I think it's, though, reasonable to conclude that this is one large area of displacement and not multiple areas. And then a third one on the 25th of August, similar story. And then 5 days before failure on the 6th of September, this is a particularly poor report. Most of the results have just been automatically masked from view. So there's nothing really to say about this report. And then, of course, the failure happened. So here are all of the contours that were reported prior to failure. First of all, you'll notice there's two here actually within the pond. So pond material, when the ground conditions permit, does move quite a bit, and we see ground displacement in the ponds whenever it's dry enough. But it's not usually of much concern to geotechs. Mostly they want to know about what's happening along this sort of outward embankment. And you can see here there's 6 contours that we detected here. This was negative displacement away from the satellite. And then 3 reports showed this positive displacement over here in the later period. And again, not to cherry pick, here are the contours site-wide. So in addition to the tailings wall and the pond that I spoke about, we have our 2 mining areas which very consistently show detectable displacement and show acceleration here. In addition, there's a couple of pairs. There's a pair of contours here and here, and these are also in actively mined areas. So not particularly surprising, not on a slope as far as I can tell. And probably real displacement, probably not false positives. So perhaps worthy of their own investigation. That's up to geotechs. And then also we have this one up here, which is harder to explain. It doesn't appear to be in this imagery based in an area of active mining. Could be real displacement, but there is a small chance it's a false positive. But I guess in conclusion, though, it's not like there are many contours here that detract from the central message that this area here is an area of significance and is worthy of investigation.
Jon, just a question on that slide. Why aren't there any acceleration polygons on the tailings wall that show up in the short-term report? And do you think that maybe would have become more evident, say, if there was high-resolution data being processed over the same area?
Yeah, good question. When you measure acceleration, you're comparing the current period to some previous period. And in a lot of ways, you're kind of adding the noise together. So when you have a lower quality site, getting displacement detections, these black contours, is, that's already a win. But to get an acceleration, you would need to be, it requires a lower noise level in general in both reports. So here, I would say this area here, the reason that's acceleration is probably very highly significant down there. It's probably moving quite fast, despite some background noise. But here doesn't quite reach our threshold, for these 2 periods to show an acceleration. I think it's worth mentioning that in the other direction, in the other set of data, the 33-degree data, I did go and look at that, and there was an acceleration detected in this area in that data. And then to speak to your other point about TerraSAR-X, with higher resolution data, you can think of it as just having many more targets on the ground. So you can think of the targets here are about 15 meters apart. But in TerraSAR-X results, they're about 3 meters apart. So there's much more opportunity to end up with a situation where you've got significant displacement in 2 periods and you end up with an acceleration, because it is actually speeding up. However, the ace up the sleeve of Displacement DataStream is not just to produce those short-term reports. We're adding a point to the time series after every single image. And the benefit of time series analysis or really the rule of thumb for InSAR in general, is the more data you solve for displacement over, then the lower the noise. And a time series can look at an arbitrarily long period. Here we see a time series going back to the start of 2021. And at the start, there's really not much going on. And then there's a period of incoherence. Perhaps this was a period of construction for this point that I'm measuring here. And then coherence returns. And then later on in 2021, we see this kind of oscillation at first, and then a very sharp acceleration, which is highly significant when you look at this length, this period of data. And because we have more data, we're able to remove more artifacts, more unwanted effects in the data. And you can see in the area, there's this yellow polygon. This is an acceleration polygon. We're saying this whole area has moved faster compared to the previous period. That's all I've got. Well, thank you very much. Any other questions, Adrian?
Yeah, thanks, Jon. I do actually I know you alluded to it, and I just want to come back to it when you spoke about the two look angles. And you mentioned that you picked the one because it was less noisy. But going back to looking at both of them, if you didn't pick one and you picked the other, looking at the long-term analysis of those two, would the two results independently, would they corroborate each other when you conduct long-term analysis? How would you decide which one to ultimately use?
Yeah, I think in a real scenario, given two footprints, I would just pick, if they were equal in every other way, I would pick the one with less noise. If there was an advantage to one incidence angle over another, then I might make my decision based on that. For instance, if I was analyzing a completely flat area, then a smaller incidence angle would work a little bit better because it would be slightly more sensitive to vertical displacement. And that's what we expect in a flat area. In this case, it was kind of, that wasn't a consideration, and I picked the 43 because there was less noise. But that was before I looked at the results, before we'd even processed the data properly. And I did notice in the 33-degree data, the other data set, that we didn't have as much of an early warning. The negative displacement that we see to the east takes a little bit longer to show up. But then when the positive displacement occurs, the bulging displacement, that is more prominent. And as I said, shows an acceleration. So instead of 4.5 months warning, I think with the other data set, we'd have got about 3 months of warning before we started detecting telltale displacement. Right,
excellent. Well, that's certainly very informative. Big thanks to Jon for the detailed analysis that you've done on this. And to those of you that have watched this, we've seen the power of InSAR using very economical data here. So, leading on from this, if any of you that are watching have any areas of concern that you think could benefit from InSAR analysis, please let us know. We'd be happy to process available data over these areas, and we'd be happy to present them to you over a call. So please feel free to reach out if this is of interest. Thank you very much for your time.
Thank you. Thanks, everyone.